Okay, so you did a, there we go, that's what we want. All right. You did a worksheet in Module 3. Just because we're starting Module 3, don't forget everything in Module 2, okay? It's all going to build on each other, and Module 2 is kind of the foundation of the whole course, talking about proportionality and constant rate of change and linearity. Okay, so this problem kind of sets the stage for Module 3. We have a sheet of paper, 8.5 by 11, and we're going to start by cutting out squares out of all four corners, and then we fold up the flaps and we make a box. So when the squares are very small, and cut out small, say 1/4 inch squares, can you imagine the type of box that you get when you do that? Shallow, and what else? And wide, right? So we can show that like this. See that? So that's like a small, when you take a small square cutout, you get a shallow wide box. And then as you make those square cutouts larger, what happens to the box? Taller, and what else? Narrower, like, yeah, so it's narrower. Taller and narrower, okay? So this is the idea. So let's talk about quantities first. Are there any, there's lots of quantities to talk about here. Are there any constant quantities? Any constant quantities we can talk about in this situation? As we look at these different boxes that we can create, is there anything that stays constant? Yeah. Okay, so one of them might be, so as I change that square cutout, notice, so here we go again. What was the original length? Yeah, we're using a standard sheet of paper, so it's going to be 8.5 by 11. So there's our 11 inch. And so notice that when I change, do you see that that dimension stays the same? From the top of the original piece to the bottom of the original piece, that dimension doesn't change. Okay? And then what about, is there anything else? Width. Okay, so from here to here. $8.5 okay? Again, notice that neither of those change. I didn't do a great job with the 11 there. That's where the 11 should start, right there. And end right there. So look at the paper. Don't look at what I drew. Look at the. Yeah, you can't look what I drew. It's gone. Anyway. So from here to here. That's our 11, and then from here to here. Notice, look at the green, not what I drew. So that stays the same as you cut out different size squares. Okay, changing quantities now. So what are changing quantities in the situation? Okay, size of the cutout. We can cut out different size squares. What else? Yeah. Okay, so that box over there on the right that's formed, changing size and shape, and so its volume is changing. So let's start with that, and there are more, we'll talk about in a second, but let's start with the side of the square cutout. And I think you called it, in the worksheet you called it X, right? So since it's a changing quantity, what we want to talk about is what are the possible values that it could take on? What are the possible values we could assign to x in this context? So, and then to do that, so that's kind of like a range of values. So we think about what's the lowest value of x and the highest value of x. So what's the lowest value of x that we can have? It's the lowest value of x we can have. Can we cut out a square that has, he said 0 side length? Can we do it? Someone says no. Just wouldn't cut one out. Is it physically possible? Okay, you ready? Get ready. I'm going to do it. I just did it. Is that amazing or what? Okay? So, yeah, you can just choose to not cut. If you choose to let x equals 0, it means you don't cut out a square. It's a perfectly legitimate situation. So here's what's not legitimate. Can we cut out a square that has an x of -1 or -5? No, negative, so that doesn't make any sense, right? But even though we don't have anything to fold up and we don't get a box, it's still physically possible and meaningful to say x equals 0. It's just you don't cut anything out and you just sit here with a piece of paper. Okay? So the lowest value of x is 0. I know it's uncomfortable because you don't get a box. But we're talking mathematically here for that quantity x. Mathematically for that quantity x, 0 is perfectly fine. Okay? And that looks like this. There's x equals 0. You end up with a flat piece of paper. But we can't make x less than 0. Okay? So now the question is, how large can we make x? How big of a square can we cut?
4.25 inches.
All right, where'd you get that? So he said 4.25 inches. Half of the width. So where is our limiting in terms of what's possible? What's the biggest square we can cut? We can't really cut anything bigger than that, right? So the shorter side is the determining factor, and if we're cutting squares out of both corners, then where we can't do it anymore is when we get to halfway. See that? So I could cut here, here and here, here and here, here and here. But then if I try to cut, say, a 5-inch square, if I cut a 5-inch square out of this corner here, then it's impossible for me to cut a 5-inch square out of this corner. You see that? So our x values, there's two ways we can write it. We can say 0 is less than or equal to x. So the question is, what about 4.25? Physically possible or not? Can we do it? Yeah, that's the situation I'm showing there. It's where you just basically you cut two squares out with the same cut right there, the same cut right here, and then you end up with a piece of paper that you just fold in half, and you get like a flat box with no width to it. So equals 4.25? Yeah, but then greater than that, so like 4.5 or 5, physically impossible to get because then you're crossing over and you're trying to cut squares like this. Can't do it. Can't do it. All right, another way to express that would be, we could express it with brackets. We could say lower value of x is 0, upper value of x 4.25. That. So both of those express the same, all possible values of x that make sense in this situation. Okay, so before we get to the volume, are there any other changing quantities? As I change the square cutout, any other quantities that change in this situation? The height changes, good, okay. Anything else? Okay, we said, okay, volume changes, that's right. Anything else? Okay, surface area of the, okay, you can do the surface area of the base, you can do the surface area of the whole open top box. Anything else? Yeah, so what about, so the width and length of the box. So if I come over here, so here's a particular square cut out. This dimension right here. This is the width. And then this dimension right here is the length. So where can we see those dimensions over on our original green sheet? Can you imagine? Let's start with this length. So the original length of the paper from here to here was 11. So up there from 11. So can you see what the length of the resulting box would be? How we would draw that here? Okay, so right, so it would be, wouldn't it be from here to here? Do you see that the width of that flap right there is the same as the width of your resulting, or the length of that flap is the same as the length of your resulting box. Do you see that? Okay, and so, and again, that's changing or constant? It's a changing quantity, right? That's a changing quantity. So how can we write it in terms of x? From here to here again was how much? 11. But it's shorter than 11, right? It's less than 11 by how much? Yeah, we're gonna you got one cutout length here of x, and you got another one down here, x. So it's the whole thing is 11, but then if the resulting length of the box will be less an x on each side, so minus 2x. Okay, similarly the width of the resulting box. We start with the fixed width of the paper. How much? How much shorter than 8.5 is it? An x on each side again. An x on each side again. So we've got 2x. Okay? And then some of you talked about volume. So the resulting volume of the box, that's what? Length times width times height. What's the length of our box? We just found it out. 11 minus 2x. What's the width? 8.5 minus 2x. So what's left is the height. What is the height of our box? Well, that's the flap, right? That's like the width of the flap, or this right here. That's going to end up being the height. What is that dimension right there? It's the side of the cutout, right? So the width of that flap, when it gets folded up, becomes the height of the box, and that's just again the length of the square cutout. So that's our height. So what I want to look at is I want to kind of compare these two formulas, these two covariations, or the ways that we got 11 minus 2x, and we got this volume relationship. If you plug x into this one, it spits out the corresponding volume. You plug x into this one, it spits out the corresponding length. So let's investigate these two. It's a nice bridge from Module 2 to Module 3. Questions on the basics of this? So the graph on the left we're going to look at the input quantity is going to be the side length cutout. This is the cutout length. Cutout side length. Okay? This one is going to be our length of the result L, the length of the resulting box. After we fold up the flaps. Then we're going to look at cutout length, again, as the x quantity. and then this was going to be the volume of the box. Fair enough? Okay. So over here, so we said that you can cut out x can be 0, right? It's okay. It's not, that's perfectly fine. We can just cut out no squares. X is 0. So when x is 0, what is the length of the quote-unquote box? Yeah, so we didn't reduce the length of the paper at all, so that's turns out to stay the same at 11. So that's what this initial point is showing. The blue arrow being the cutout side length, and we're starting at 11. Okay, so now I want to do a change of. I'm going to do a delta x. Look at some delta x and delta L. Now, these won't be ordered pairs on this graph, right? Two different sets of quantities. Here I'm looking at L and x, but my ordered pairs are delta L and delta x, right? So these ordered pairs won't be points on this graph because it's different quantities, right? So I'm going to do a delta x of 0.5. What does that mean? It means I'm going to cut out squares along the length here of 1/2 inch each on either side. What will the resulting length be when I do that? Or sorry, what will the change in length be? So how much, that's what we want to ask. If I increase the cutout length by 0.5, or in this case just make squares of 0.5, how much will the length change?
-1.
Okay, so lots of you are saying 1, and some in the front said -1. Should I put 1 or -1 here? It's gonna go down by 1, right? So let's show that. So here, let's try to show that. Come on. I just increased the side length by 1/2, and what happened? The length went down a whole unit because of 1/2 on each side. What if I did that again? What if I now made the square cutout 1/2 inch larger than before? How much would the length go down? I'm going to do the same thing again. I'm going to change the cutout by 1/2. How much will the length change? Yeah, the change in length will still be -1. So if I increase my squares, the cuts in my squares by 1/2 inch, it went down another 1. So I increased by another 1/2, and it went down another 1. What if I increase the square cutout by 1? So now I'm at this given place where I have these square cutouts. I'm going to increase the size of the square cutout by 1. That's what delta x means. How much will the length change? -2, right? Will that always happen? So here's an increase of 1 right there. Boom. Cutout went down. Sorry, I'm trying. Jeez. There. Okay. So I went down by, or I increased the square cutout by 1. Length went down by 2. What if I do that again? I'm going to increase the square cutout from 2 to 3. How much did the length go down? It went down 2 again, right? Now I'm going to increase the square cutout by 2. How much will the length go down? Want to go down 4? So where I'm at 3, so I'm going to increase the square cutout up to 5. And the length, you saw the length go down. I'll draw that one. I'll draw that one. We were at 3, and was it 5? What did I do? I just increased the cutout length by 2, and the result was before that, when I increased the cutout length by 1. What happened? Length went down 2. In fact, no matter what, how can I always get, if I know how much I increase the square cutout length by, how can I always get the resulting change in length? What can I do? 2 times x?
11 minus 2x. Oh,
Okay, so I heard 2x, I heard 11 minus 2x, negative 2x. One of those or something different? It's none of those. Negative 2 times delta x, right? Negative 2 times delta x. It's always negative 2 times delta x, no matter what the delta x is, and no matter where I choose to apply that delta x, my change in length is always negative 2 times that. Why? Because you're taking out 2 of them. And so if you're going to increase a little bit on 2 sides, the decrease in L will be twice the increase of 1 square. That's what we're saying. Anybody have a question on that? All right, compare it to the volume. So when our cutout is 0, what volume do we have? That's the flat piece of paper scenario, right? We got, when x is 0, we don't cut squares out, we got a volume of 0. Now I'm going to do a change of volume, or sorry, of cutout of 1, just like I did on the other one. So delta x is going to be 1, and specifically I'm changing from 0 to 1, okay? X goes from 0 to 1. What will the corresponding change in volume be? How can we find it? So I'm going from flat piece of paper to increasing the cutout length by 1 inch. And I want to know how much does the volume change. How can we find that? How can we find that? Yeah.
by creating a formula for D.
Okay, so we did create that formula. Remember what it was?
Yeah, it should be 4x to the third minus 39. Oh, yeah.
And those,
I just multiplied it all together.
yeah. So, but this
0.5 minus 2x times x.
this form is nice because it really conveys the meaning of that volume of that box, right?
Yeah.
Length times width times height. So how can we get this change in volume that results when we increase the side length by 1? The cutout length. How can we get it? Yeah, plug 1 in. Because we just went from 0 to 1, we want to know what's the volume at a 1 inch square. So do it. What do you get?
58.5.
58.5. Okay, so when delta x is 1, delta v is 58.5. Let's watch it. Here we go. Boom. When we increase, so what you saw, when I increased it 1, the volume went up 58.5. Okay, so now, if I do that same amount of increase, I'm going to do another delta x of 1. But this time, I'm going from 1 to 2. But it shouldn't matter, because every time I increase delta x by 1, the volume is going to go up the same amount, right? So the volume now is going to go up another 58.5 this time, right? As I change the squares from 1 to 2 inches. Yes or no? Let's see. I'm going to increase the squares from 1 to 2 inches, meaning another delta x of 1. And did the volume go up 58.5? How much did it go up? Can you figure it out? Figure out how much the volume went up. when I made x go from 1 to 2. Again, it's another delta x of 1, but a different delta x. Figure out how much the volume changed. Just go. Figure it out. Okay, someone want to volunteer? Someone in the back. What did you do to find this change in volume as the cutout size increased from 1 to 2? Yes, sir. Okay. And what did you get for that? Good. Okay. Good. Right, so here's our delta x of 1. So our delta v, you're going to find by? What was it? He said he subtracted 63 minus 58.5. Right? So we had a delta x of 1, and we got a change in volume of 58.5. Then we had another delta x of 1, and we got a totally different change in volume, 4.5. I thought it was always supposed to be the same. I thought equal changes in x were supposed to result in equal changes of volume. Right? Didn't we say that? Was there a question up here?
I answered
The answer. Okay, cool. So what's happening? What's going on here? I thought, aren't equal changes of x supposed to be equal changes of y? What's that? What's constant? Yeah, she's onto something here. What do we have here that we don't have here? Okay, and what kind of covariation is that?
Our proportionality is what I would say.
First,
It's not
linear. Okay.
Constant.
Constant rate of change. That's the buzz, right? So, what's proportional? Are x and L proportional? No, x and L are not proportional. Changes are proportional. When the changes are proportional, this is what? Constant multiple reasoning of proportionality. When the changes are proportional, we have constant rate of change and we get a linear graph. Right? The change in L is always -2 times whatever change in x you put in there. Always. That's constant rate of change. Okay? So, do we have constant rate of change over here? Not even close, right? Because there's no way we could never write a formula like this. For this graph. There's no constant such that for every delta x, it's the change in v is just a constant times it. There's no constant multiple reasoning or proportionality of changes there. No proportionality of the changes of the quantities. Do it one more time. So let's let x increase from 2 to 4. Okay? So let it increase from 2 to 4. Find the change in volume. Practice. So now I want to do a change of x of 2. X going from 2 to 4. Find the corresponding change in volume.
You want
Okay, we're filling this table in. So what do I want?
You want negative 57.
Change in volume, right? Change in volume. What did you get?
Negative 57.
And how'd you get that?
I plugged 4 in and subtracted it from what 2 is equal, so I got 6, and I subtracted that from 63.
So when we choose cutouts of side length 4, he's saying the volume ends up being 6. Is that right? So what's the change? How do you find the change in V? Subtract. And we're going to get? If you said 57, you're incorrect. It's always final volume or final version of the quantity minus the starting value of the quantity. So the final minus the initial, 6 minus 63 is 57, negative 57, indicating that over that change in x, the volume goes down that much. Yeah, question?
Plug in both because, like, you plug in the 2 and the 4 because each one gives you a different volume, so you have to.
That's right. So here we are at 2. Let's just write this ordered pair. What was this? This is the volume at 2 is 63. And then we increase the volume up to 4. And now at 4, what's the volume? What does this box look like, by the way? Narrow and tall. 4, 6. So, shoot. So here's our 2. So we have a change of x of 2. And then we have the corresponding. Let's see how we can do here. One time. I started in the wrong place. Anyway, that should be straight and vertical. So from here to here is that change in volume. How would you calculate that? See that? From that starting volume up there down to this volume, how would you get that length of that segment? What would you do? Yep, you would take, it would be what? 6 minus 63. Final volume minus initial. So here, here's the thing with this. We have to do it this way. We don't have a formula like this where we can crank out the change in y given the change in x without even thinking. We've got to figure out the final volume and the initial and subtract because we don't have constant rate of change. You see? If we have constant rate of change, then we've got this proportionality of changes, and we can just crank out delta L's given any delta x. But if you don't have constant rate of change, then you've got to find the final value of your quantity and the initial value and subtract. Again, we don't have something like this to give us changes in volume for a change in x. Okay. See how much there is to talk about just about this one problem, okay? And everything's important. Any questions before we go on? So let's look at this idea that when you have a formula that where is it? Here we go. So this idea that you have a formula that you can plug these values into, these quantities, these side length quantities, and it spits out a volume, that's the idea of what we call a function. Okay? Your phone has, just the phone part of your phone has a function. What do you do to it? You give it a number, right? Domino's Pizza, your mom, your boyfriend, your girlfriend, whatever. So you put that number in, and it has a function. What does it do? Connects you with that person, right? It connects you with that person or that business or whatever it is. Same thing with this. It has a function. It takes the square cutout length and it gives you a volume. That's what this one does, okay? It gives you a volume, right? So it has a purpose. It has a function to take something. You're going to give it something and it's going to spit something out. Quantities, right? The value of one quantity you give it, it gives you the value of another quantity. So here are the parts. So let's just go on. I'll do that in a second. So it's the idea of a machine, okay? The idea of a machine. This machine takes the length of a cutout. If you give it a number, it interprets it as the length of a side of a cutout. It cranks on it, and its purpose is to give volume. That's its function. That's its function, right? More generally, what we call input is what we give it, and output is what it gives us back. And the rule is what determines the output given the input. Okay? This is the idea of a function. So here, the output is volume. This letter, often F, but can be anything, that's called the name of the function. All right? That's the name. The input then is in the parentheses. Inside the parentheses is the input, and then most of the time, that's also part of what's called the rule. Okay? So that's the rule. The rule is kind of the guts of the machine. It takes it's the thing that takes the input and makes the output out of it. But here's the tricky thing about this. This is the notation that we'll use most of all. Notation like this. Of all this stuff that we just went over, of all these different things, what is what's inside the blue box equivalent to? What is that? What does that represent of all these things? Is it the output? Is it the name? Is it the input? Or is it the rule? It's the output, okay? Whenever you see that notation, it's representing the output of the function named, in this case, named f, with an input of x. So it's a very convenient way to represent values rather than cranking them through the rule. Instead of finding the number, we can just represent it this way. We can just write f of x, and that represents the output. So for instance, what does this represent?
No, it represents when you put 2 in.
Does it represent a square cutout of 2?
Yes.
No, it doesn't. Does it represent a volume of 2? No. Does it represent a square, first of all, a volume or a square cutout?
Square cutout.
No. It's a volume. It's the output. F of 2 is the output of the function, so it's a volume. But which volume is it? Volume of the box when the cutout is 2. So this is the volume of the box when the cutout is 2. When the cutout has side length of 2. Does it make sense? So we're going to practice that a lot, but before we do, next time, and so the rest, we got one more week before the exam is a week from Thursday. So until then, we're going to be doing lots of work with this function notation, okay? It's really important. So I think we are ready for Top Hat. Let's do it.